Let's talk about gravity and energy. Equations for energy, according to Newton, are, according in fact to classical physics, are that kinetic energy equals half the mass times the velocity squared. Potential energy, if you integrate Newton's equation for force, is equal to the product of the masses involved, universal gravity constant G, and the difference between the two distances over which the potential energy is measured. So if this is the Earth's radius and this is the orbital radius of the Moon, this would be the energy between the Moon and the Earth. Now the trouble is, one of the problems is that energy is a function of mass of just the Moon or any other moving object. This is the product of the masses of the two bodies. Now, if you drop something on when the Moon is or was traveling away from the Earth, and the kinetic energy is being converted into potential energy as it goes, how do you convert one to the other when they appear to be defined somewhat differently? Well, we found part of the answer to that on the last video, where we showed that G contains in its denominator the mass of the Earth, or the mass of the central body, which takes away the mass of the Earth, or rather compensates for it. But that doesn't mean to say that the Earth's mass does not enter into the potential energy equation. It obviously does, but it remains in G because of G's definition, or rather its dimensions, which are length cubed divided by mass divided by a period squared. And that period, there's the mass of the Earth, which cancels out the mass of the Earth in the equation for potential energy, but the period depends on the mass of the Earth still. So you still have that compensation, but nonetheless, it is rather worrying that one equation appears to ignore the mass. And in fact, it's not valid to say always that the kinetic energy is equal to half mv squared. And the reason for that is that it is based on the assumption, which is normally is all right, that you can ignore the mass of the Earth because it's so large that it gets very little of the kinetic energy. But to balance it, to get the correct balance, you should take the mass of the two bodies, take the Earth and the Moon. The Earth will say a mass 1 and the Moon a mass 2. When the Moon orbits the Earth, what's really happening is that they are both orbiting around their centers, the combined center of mass, so that the Moon goes round in a very large orbit and the Earth goes round in a smaller orbit. It's not that small because the Moon is only about 30 times lighter than the Earth, and so there is a significant movement of the Earth. And that, of course, absorbs kinetic energy. So the true kinetic energy of this system is half of the mass of the Earth multiplied by the velocity with which we'll say it's traveling, v1, plus half the mass of the Moon times the velocity with which it is traveling, which will be in the same orbital direction but opposite direction, like that. So there are two masses in this is the total kinetic energy of the system. but they're not multiplied as together as they are. The two masses are not multiplied as they are in potential energy, and it just seems strange that you can convert the one to the other. So in looking into that, I came up with an idea for creating not a new definition for kinetic energy, but another way of looking at it, and potential energy. And this seems to fit in better with the way in which gravity works. And the way that this works is that if you take what I've referred to many times as the energy shell, which has several dimensions, but we can look at two dimensions there. Well, what I call the x dimension and the space dimension. When the Earth and the Moon are in a circular orbit, then the orbit is around here. Looking at it from the side, it would be like this. But from the front, or from this side here, which is another space dimension, you see just a line. But when you look at it from this angle, you see a circle, and that is the circular orbit of, or roughly circular orbit of the Moon. But drawn this way, we can separate the kinetic from the potential energy, because the potential energy is in this dimension here, and the kinetic energy is in this dimension here. The coordinates for x are equal to the period, which is the time it takes to orbit 1 radian, times the velocity, dr by dt. And so that is a measure of the kinetic energy in this direction, the potential energy there, and this is the total energy, which corresponds to the radius of the energy circle. And if you look at the equations there for kinetic energy and potential energy, they look like this. They look like that you have to have the product of the masses, because that tells you how much multiplication you get from the masses. It's not to do with the way that energy functions, or that gravity functions. It's just a multiplication factor, the product of the two masses, because that gives you the extent of the relationship. That times r squared, which is the radius of the energy circle, is equal to the orbital velocity squared, circular velocity, times the period squared, the period in a circular orbit. And that is, it looks as though I just made that up, but I didn't really, because if you look at it, you take half mv squared and say that that's equal to mmg, where g is r cubed divided by mass divided by torr squared times the reciprocal, or the difference between the radii. If you multiply both sides by mt squared, you get over here mv squared t squared, the period squared, multiply both sides by 2, and you get 2 r cubed, and here you have the difference in the radiuses. And you see that's not very different from that equation. Dimensionally they're identical, because you have over here r squared, well that's the other way around, of course, r squared this side. But as you see, it's not that far out. And the big advantage is that it now gives you the right proportions to that diagram, because that shows that the kinetic energy and the potential energy vectors, they're really what I call energy equivalent lengths, because they're lengths that represent energy. This is the total energy. It's the sum of the squares, and as you see, the kinetic energy is much larger than you would have thought, because you see, when we use Newton's equations, if you have the moon going as far as that initially, and then settling into a circular orbit here at half the initial radius, well, that's where it went up to first, you can see that that amount of kinetic energy goes in, or that amount of potential energy goes into the kinetic energy of the revolution of the orbit, and thus you keep the same energy. And this is quite small, being so far from the Earth. This is quite small, and only a small percentage of the and that corresponds with the small orbital velocity. So, so I think that this examination of energy that I've carried out in the past few weeks is yielding some information that may turn out to be useful. So that's enough for this video. Thank you.